Hello, my friend, and welcome to Orbital Dreams. Look around you for a moment. The room feels ordinary. The air feels empty. Space feels simple, just height, width, and depth. But what if that emptiness has a hidden depth? What if reality has layers we cannot see, folded so carefully into the world that we have lived beside them forever without noticing? Hidden dimensions may be a secret part of space itself. And if they are real, then the world around you may be only the surface of something much deeper. This is the mystery of hidden dimensions. Tonight, we'll gently explore why some physicists think reality may be larger than it looks, how extra dimensions could be hidden inside space itself, and what it would mean if the universe around us is only the visible surface of something much deeper. So get comfortable, let the day fade away, and let's begin. Chapter 1. The strange possibility of more than 3 dimensions. To understand hidden dimensions is to ask whether the reality around you is only the visible layer of a deeper structure. And that single question reaches into the foundations of space, time, gravity, and the shape of the universe itself. At first, the idea may sound almost impossible. We live in a world where things have height, width, and depth. You can move left or right, forward or backward, up or down. Every room, every road, every body, every planet seems to fit inside this familiar 3-dimensional space. It feels complete because it is the only kind of space our senses have ever known. And yet, science has often moved forward by questioning what feels complete. The Earth once felt motionless. The sky once seemed like a dome above us. Time once seemed to pass at the same rate everywhere for everyone. Each of those ideas felt obvious because human experience supported them. But when observation became sharper and mathematics became deeper, reality turned out to be stranger than common sense. Hidden dimensions belong to this same family of ideas. They are not something that has been proven to exist, but they are also not random fantasy. They are a serious possibility that appears when physicists try to understand the universe at its most fundamental level. A dimension, in simple terms, is a direction or an independent way something can vary. A line has 1 dimension because you can move only along it. A flat surface has 2 because you can move across it in 2 independent directions. The space around you has 3 because any position can be described by 3 directions. But mathematics does not stop there. It can describe spaces with more dimensions than we can picture. These higher dimensional spaces are not easy to imagine, but they can be handled precisely with equations. In physics, that matters because many real things were first understood mathematically before they became intuitive. The strange part is that extra dimensions do not have to be large, open directions like the ones we experience. They might be hidden because they are shaped in ways that ordinary perception cannot access. A simple analogy is a thin wire seen from far away. From a distance, it may look like a 1-dimensional line, stretching only forward and backward. But an ant walking on the wire would discover another direction, around the wire's tiny circular surface. That direction was always there, but it was too small to notice from far away. In a similar way, some theories suggest that extra dimensions could be curled up so tightly that ordinary matter and light do not reveal them directly in everyday life. This does not mean that hidden dimensions are tiny rooms beside our own, or secret corridors floating somewhere in space. That image is dramatic but misleading. A hidden dimension would not necessarily be a place you could enter with a spaceship. It would be part of the structure of space itself. It would be woven into every point, not lying beyond some distant border. If extra dimensions exist in this way, then they would be present here, in the quiet room around you, in the space between atoms, in the structure beneath every ordinary object. They would be hidden not because they are far away, but because they are inaccessible to the scale and motion of our everyday experience. One reason scientists take this idea seriously is that the laws of nature seem deeply connected to geometry. Gravity, in modern physics, is not treated simply as a force pulling objects across an empty stage. It is described as the curvature of spacetime. Massive objects such as stars and planets shape spacetime, and other objects move along paths influenced by that shape. This was already a profound change in how we understand reality. It meant that space and time were not just a background. They had structure. They could bend. They could stretch. They could influence motion. Once physics accepted that geometry could explain something as powerful as gravity, it became natural to ask whether a richer geometry might explain even more. Perhaps some features of the universe that appear separate to us are actually different aspects of a higher dimensional structure. This was one of the motivations behind early ideas of extra dimensions. Physicists wondered whether forces that seem different in ordinary space might become connected if space had more directions than we can see. The goal was not to make reality stranger for its own sake. The goal was unity. The hope was that a deeper view of space might reveal why nature has the laws it does. This is one of the most important things to understand about hidden dimensions. They are not added casually. In serious physics, extra dimensions usually appear because a theory is trying to solve a real problem. They may help organize forces, explain particle behavior, or make mathematical descriptions consistent. In string theory, for example, extra dimensions arise because the theory's internal structure requires more than the familiar dimensions of space and time. Whether string theory describes the real universe is still an open question, but its use of hidden dimensions is not arbitrary. It comes from the mathematics of trying to combine quantum physics with gravity. Quantum physics describes the small world of particles, atoms, and fields. General relativity describes gravity, space-time, and the large-scale universe. Both are extremely successful in their own domains, but they do not fit together easily in the most extreme situations, such as the heart of a black hole or the earliest moments of the universe. Hidden dimensions appear in some attempts to bridge that gap. They offer a way to imagine that what we see as separate physical effects may come from a deeper, more unified structure. Again, this is not confirmed truth. It is a possible path, but it is a path taken seriously because the problems it addresses are real. For an average person, the difficulty is not only scientific. It is imaginative. We are built to survive in a three-dimensional world. Our eyes detect light from surfaces. Our hands touch objects with volume. Our inner ear helps us balance in gravity. Our brains create a stable picture of space because that is what daily life requires. We do not need to visualize higher dimensional geometry to pour water, open a door, or walk across a street. So when science asks us to imagine more dimensions, it asks us to step outside the limits of ordinary intuition. But there is a gentle way to approach it. Instead of trying to picture an extra dimension directly, we can think about how a creature in fewer dimensions might struggle to understand us. Imagine a world that exists only on a flat surface. A being living there could move left and right, forward and backward, but never up or down. If a sphere passed through that flat world, the being would not see the whole sphere. It would see a circle appear, grow larger, shrink, and disappear. The full three-dimensional object would be real, but the flat creature would experience only slices of it. In the same way, if higher dimensions exist, we may be experiencing only a limited slice of a larger reality. This idea is powerful because it changes the meaning of the word hidden. Hidden does not always mean invisible in the ordinary sense. It can mean that something is beyond the categories our senses are designed to detect. You do not see magnetic fields directly, yet they can shape matter. You do not feel space-time curvature as a visible substance, yet it guides planets around stars. You do not see the quantum fields underlying particles, yet modern physics treats fields as deeply fundamental. Hidden dimensions, if they exist, would belong to this deeper layer of reality. Not magical, not supernatural, but structural. Of course, science must remain careful. A beautiful idea is not enough. A mathematical possibility is not the same as evidence. At present, there is no confirmed experimental proof that extraspatial dimensions exist. Physicists have looked for possible signs in particle experiments, gravity tests, and cosmological observations, but hidden dimensions remain hypothetical. This uncertainty is not a weakness of science. It is how science protects itself. It allows imagination, but it also demands evidence. It lets us explore bold possibilities without pretending that all possibilities are facts. That balance is what makes hidden dimensions so fascinating. They sit between what is known and what might be known. They are close enough to serious physics to deserve attention, but far enough from confirmation to remain mysterious. They remind us that the universe may not be limited to the shape our senses present to us. The familiar world may be real, but incomplete, like a page from a much larger book. And perhaps this is the most calming part of the idea. You do not need to solve the mystery tonight. You do not need to picture every dimension or understand every equation. For now, it is enough to rest inside the strange possibility that reality may be wider, deeper, and quieter than it appears. So let the day loosen its grip. Let the familiar room around you become soft and still, and imagine that even ordinary space may be holding more silence, more depth, and more mystery than the waking mind can ever fully carry. Chapter 2. What we mean by a dimension. A dimension is one of the quietest ideas in science, yet almost everything we know about reality depends on it. Before we can ask whether hidden dimensions exist, we first have to understand what a dimension actually means. The word sounds simple because we use it casually. We speak of the dimensions of a table, a room, a box, or a screen. In ordinary language, dimensions often mean measurements. How long something is, how wide it is, how tall it is. But in science and mathematics, the idea is deeper. A dimension is not just a size. It is an independent way something can vary, move, or be described. Begin with the simplest possible case. Imagine a perfectly straight path. A bead sliding along that path can move forward or backward, but it cannot move sideways, upward, or downward if it is truly confined to the path. To locate the bead, you need only one piece of information: where it is along the line. That is what makes the line one-dimensional. The bead may have many properties, such as color, mass, or temperature, but its position on that path requires only one independent direction. Now imagine a flat surface, like a sheet of paper. A tiny dot moving across the paper has more freedom. It can move left and right, but also forward and backward across the surface. To describe where it is, one piece of information is no longer enough. You need two independent measurements, such as how far across and how far up the page. That is the idea of a two-dimensional surface. It is not just that the paper looks flat. It is that motion on the paper requires two independent directions. The space we experience every day adds another layer of freedom. A bird in the air, a fish in the sea, or a dust particle floating in a quiet room can move left and right, forward and backward, up and down. To describe its location, we need three independent directions. This is the familiar three-dimensional space of daily life. It is the space of furniture and planets, of bodies and buildings, of hands reaching through air and light crossing a room. But the most important part is the word independent. A dimension is not simply any direction you can name. It is a direction that cannot be built from the others. On a flat map, moving northeast is possible, but northeast is not a new dimension. It is a mixture of northward motion and eastward motion. The basic dimensions are the independent ones, the directions from which other directions can be combined. This is why physicists and mathematicians care so much about dimensions. They tell us how many basic pieces of information are needed to describe a position, a motion, or sometimes an entire state. There is another subtle point. Dimension does not always depend on how something looks from outside. A long thread lying on a table may curve, twist, and loop around. But if a tiny creature could only move along the thread itself, its world would still be one-dimensional. Its path might bend through three-dimensional space, but the creature's freedom of motion would be only forward or backward along the thread. In the same way, the surface of a sphere is two-dimensional for a creature that lives only on that surface. The surface may curve through a larger space, but the creature does not need a third surface direction to locate itself. It can use two measurements across the surface, such as something like latitude and longitude. This helps separate two ideas that are easy to confuse: the dimension of a thing and the space around the thing. A drawing on paper may represent a cube, but the drawing itself is flat. A road may twist through hills, but if you're constrained to drive along it, your possible motion follows one main path. A planet's surface may be curved, but a point on that surface can still be described using two independent surface directions. Dimension is about freedom and description, not only appearance. This is why mathematics can talk about dimensions we cannot easily picture. A higher dimensional space does not have to be imagined as a strange visible object floating somewhere above us. It can be understood as a system that needs more independent information to describe it. For example, if you want to describe not only where a moving object is, but also how fast it is moving and in what direction, the full description becomes richer than ordinary position. Scientists often use abstract spaces where each dimension represents a different measurable quantity. These spaces are not rooms you can walk through. They are ways of organizing information. This may sound like a trick, but it is one of the great strengths of science. Many ideas that are hard to visualize become clear when treated as relationships between quantities. Temperature, pressure, electric charge, spin, energy, and momentum are not directions in ordinary space. Yet they can be represented mathematically as parts of a larger description. When scientists say a system has many dimensions in an abstract sense, they may not mean there are many physical directions, like left, right, up, and down. They may mean that many independent quantities are needed to specify what the system is doing. For the topic of hidden dimensions, however, we are especially interested in physical dimensions, possible directions of space, or aspects of spacetime that could belong to the structure of the universe itself. To approach that idea carefully, we need to remember that a dimension is not necessarily something our senses can isolate. Our eyes do not see dimension directly. They receive light, contrast, motion, and shadow. The brain builds a three-dimensional model from these clues. Touch gives pressure and resistance. Balance gives orientation. Movement teaches the body how space behaves. The feeling that space has three dimensions is deeply reliable in everyday life, but it is still a model built by biology and tested by experience. Science refines that model. In classical physics, space can be treated as a stage with three independent directions, and time as a separate flow that tells when events happen. This picture works extremely well for slow speeds and ordinary scales, but modern physics changed the relationship between space and time. Time is not simply an outside clock ticking the same way for everyone. Measurements of time and space depend on motion and gravity. This is why physicists often speak of spacetime, where events are described not only by where they occur, but also by when they occur. An event is something that happens at a particular place and a particular time. A spark flashing in the dark, a footstep touching the ground, a photon arriving at a detector. Each event needs spatial information and time information. In ordinary language, we separate the where from the when. In modern physics, they are connected in a single structure. This does not mean time is exactly the same as a direction of space. You can choose to walk left, but you cannot choose to walk yesterday. Time has a different character. Still, it functions as an essential dimension in the description of physical events. This matters because it teaches us humility. Even the dimensions we know best are not as simple as they first appear. Space and time are not merely empty containers. They are part of the physical description of the world. They shape how motion is measured, how gravity is understood, and how events relate to one another. Once this is accepted, it becomes easier to see why scientists might ask whether the dimensional structure of reality has more to it than ordinary experience reveals. Another useful way to understand dimension is through constraint. A train on a track has less freedom than a car on a wide road. A car on a road has less freedom than a drone in the air. The object with more freedom needs more information to describe its possible motion. In this sense, dimensions are tied to possibility. They define what kinds of movement, change, and relationship are available within a system. A world with different dimensional structure would not merely look different. It could have different kinds of motion, different kinds of stable forms, and perhaps different physical laws. This does not mean that every mathematically possible dimension must exist physically. Mathematics is wider than nature as we observe it. It can describe possibilities that may not correspond to our universe. But physics often uses mathematics as a lantern, exploring structures that might explain what experiments reveal. The concept of dimension gives that exploration a precise language. Without it, the idea of hidden dimensions would be vague. With it, the question becomes sharper. How many independent directions or degrees of freedom does reality truly have? And are all of them accessible to us? For now, the safest answer is that everyday space behaves as if it has three large spatial dimensions: while time is inseparably involved in the description of events. Hidden dimensions, if they exist, would have to be arranged in a way that explains why they do not show up in ordinary motion and measurement. That is the mystery waiting ahead. But before reaching it, it is enough to hold the simple meaning clearly. A dimension is a basic, independent way for something to be located, to vary, or to be described. And as you rest with that thought, the world around you can feel a little softer. The room is still the same room, the night is still the same night, but beneath its familiar shape lies a quiet idea. Reality has structure, and understanding even one small part of that structure can make the universe feel less chaotic, more ordered, and gently immense. Chapter 3. Why 3 dimensions feel so complete to us. 3 dimensions feel complete because every moment of ordinary life trains the brain to trust them as the full shape of reality. Before we ever learn the word dimension, we already live inside height, width, and depth. We reach toward objects, avoid corners, climb stairs, pour water, judge distance, and turn our heads toward sounds. The body does not treat space as a puzzle. It treats space as the quiet background of survival. By the time we are old enough to think about physics, 3-dimensional space already feels less like an idea and more like common sense. This feeling begins with the senses. Human vision does not simply record the world like a flat picture. Each eye receives a slightly different view because the eyes are separated by a small distance. The brain compares those 2 views and uses the difference between them to estimate depth, especially for nearby objects. This is part of why a hand reaching toward your face feels close, while a tree across a field feels far away. But binocular vision is only one part of the story. Even with one eye closed, the brain still reads depth from many clues. Objects partly hiding other objects, parallel lines appearing to converge in the distance, familiar things looking smaller when they are farther away, shadows revealing shape, and motion changing the view as we move through a room. The world feels 3-dimensional because the brain is constantly building depth from patterns. It is not passively receiving space. It is interpreting light, movement, memory, and expectation. A flat image on a screen can create the impression of depth because the brain recognizes the same visual clues it uses in the real world. A road narrowing toward the horizon, a face lit from one side, or a room drawn with perspective can all make a flat surface feel spacious. This shows how strongly the brain is tuned to 3-dimensional structure. It searches for volume almost automatically. Touch makes that feeling even stronger. Vision can be fooled by images, but touch adds resistance, texture, temperature, and shape. A cup is not only seen as an object with depth, it is grasped. The fingers curve around it. The hand learns its thickness, its weight, its rim, its hollow inside. A wall is not only a colored surface, it stops the body. A chair supports weight. A stone has edges, mass, and firmness. Through touch, the body confirms that objects occupy space and that this space has directions in which movement is possible and directions in which movement is blocked. Movement is perhaps the deepest teacher of all. A person does not understand space only by looking at it. A person understands space by moving through it. Infants slowly learn how far away things are by reaching, missing, trying again, crawling, standing, falling, and balancing. The brain links visual changes with bodily motion. When you walk toward a door, the doorway grows larger in your field of view. When you turn your head, the room shifts predictably. When you step around a table, its hidden side becomes visible. These patterns become so familiar that the mind stops noticing them. Space feels obvious because the body has spent years testing it. Gravity also gives space a strong sense of orientation. We do not experience all directions equally. Up and down are not just geometric directions to us. They are bodily conditions. Down is where unsupported things fall. Up is where effort is required. Balance depends on knowing the direction of gravity. The inner ear helps detect acceleration and head position, while muscles and joints report how the body is arranged. This creates a steady sense of verticality. A room can be measured in any direction, but to a living body, the vertical direction has special meaning. It organizes posture, walking, lifting, and rest. This is one reason 3 dimensions feel so natural. They are not abstract to us. They are tied to action. Width is where the arms can spread. Height is where the body rises. Depth is where the path continues ahead. Space is not first encountered as a coordinate system. It is encountered as possibility, where the body can go, what the hands can reach, what the eyes can follow, what the feet can step onto. A creature shaped differently, with different senses and different movement, might build a different intuitive picture of the world, even if it lived in the same physical space. The brain also simplifies reality in useful ways. It does not show us every physical detail available. It builds a stable working model that helps us act quickly. We do not see every wavelength of light. We do not hear every vibration in the air. We do not sense the magnetic field of Earth the way some animals appear to use it. Our perception is not a complete copy of nature. It is a survival-oriented interface. It gives us the information that mattered most for moving, finding food, avoiding danger, recognizing faces, and using tools. For human beings, the large-scale world is overwhelmingly 3-dimensional. Animals move through 3 large spatial directions. Objects have volume. Light travels through space and reflects from surfaces. Sound spreads through air. A thrown object follows a path we can track. The fact that this world works so consistently reinforces the feeling that 3 dimensions are all there could be. The idea becomes buried inside ordinary experience. It is not something we prove every morning. It is something the world keeps confirming with every step. But this sense of completeness has limits. It is based on the scale at which we live. Human bodies are neither as small as subatomic particles nor as large as galaxies. We inhabit the middle world of tables, rain, roads, trees, mountains, and visible skies. At this scale, 3 spatial dimensions are enough to describe nearly everything that matters for daily life. You do not need extra dimensions to walk across a room. You do not need them to understand why a ball rolls under a sofa. You do not need them to build a house, cook a meal, or look at the moon. Everyday success makes our picture of space feel final. Science has shown many times that everyday success can hide deeper structure. Matter feels solid, yet atoms are mostly empty space shaped by forces and quantum behavior. The ground feels still, yet Earth rotates and orbits the sun. Time feels universal, yet its measurement depends on motion and gravity. In the same way, the completeness of 3-dimensional space may reflect the scale and conditions of human life rather than the full architecture of reality. This does not mean extra dimensions exist. It means that our feeling of completeness is not proof that they cannot exist. The challenge is that the brain cannot easily imagine a direction outside the 3 it uses for ordinary space. We can understand the idea symbolically, but we cannot picture it, the way we picture left, right, up, or forward. The mind tries to turn higher dimensions into familiar images, shadows, layers, folded surfaces, or hidden rooms. These images can help, but they are only approximations. They translate a difficult idea into something our three-dimensional intuition can hold. The real mathematical concept may not look like anything the imagination can fully display. This limitation is not a failure of intelligence. It is a sign that imagination evolved for practical space, not for every possible geometry. A person can understand that there are colors beyond visible light without seeing them. A person can understand that there are sounds beyond human hearing without hearing them. In the same way, a person can understand that higher spatial dimensions are mathematically possible without being able to visualize them directly. The boundary lies not only in nature, but in the design of our senses. Three dimensions also feel complete because language and culture reinforce them. We describe the world in terms of near and far, above and below, inside and outside. Our buildings, maps, games, machines, and stories all assume the same spatial framework. Even when we imagine impossible worlds, we usually imagine them as strange things happening inside three-dimensional scenes. Our dreams, memories, and plans unfold in spaces with bodies, objects, paths, and horizons. The mind keeps returning to the structure it knows best. Yet there is something beautiful in this limitation. The fact that we cannot naturally see beyond three dimensions does not trap science. Instead, it gives science a frontier. Mathematics allows thought to move where perception cannot. Experiments allow nature to answer questions that intuition cannot settle. Theories of hidden dimensions begin precisely at the edge between familiar space and deeper possibility. They ask whether the world that feels complete to the body might still be only part of a larger structure. So when three dimensions feel obvious, they are not wrong. They are real in the domain of ordinary life. They are the dimensions in which bodies grow, rivers flow, homes are built, and stars appear in the night sky. They are the space of human experience, and they deserve their feeling of completeness. But science gently reminds us that feeling complete is not the same as being complete. Reality may be larger than the shape that life has taught us to expect. For now, you can rest inside the three dimensions you know so well. The bed beneath you, the room around you, the quiet distance between your thoughts and the stars, all belong to this familiar space. Let it feel steady. Let it feel simple. And if reality holds more than the senses can reach, there is no need to chase it tonight. It can remain softly hidden, waiting beyond the edges of imagination, while the day slowly fades away. Chapter 4. Time as the fourth dimension. Time becomes one of the most profound ideas in hidden dimensions because it shows that reality can have a deeper structure than ordinary experience suggests. In daily life, time feels different from space. Space is where things are. Time is when things happen. You can walk across a room, turn around, and return to the same chair. But you cannot turn around and walk back into yesterday. You can choose to move left or right, forward or backward, up or down, but you cannot choose to move freely through time in the same way. This makes time feel less like a dimension and more like a river carrying everything forward. For most ordinary situations, that feeling is useful. We remember the past, experience the present, and anticipate the future. We plan, wait, age, and change. Clocks measure regular processes, such as the swing of a pendulum, the vibration of atoms, or the turning of Earth. In everyday thinking, time seems to be a universal background, flowing at the same rate everywhere. A minute in one room seems like a minute in another. An hour on the ground seems like an hour in the sky. Common experience tells us that time is shared by all observers, like a silent rhythm beneath the world. Classical physics was built in a way that mostly matched this intuition. Space could be described as a stage with three independent directions, while time acted like an external clock. Objects moved through space as time passed. A falling apple, a rolling wheel, or a planet orbiting the sun could be described by asking where it was at each moment. In this view, time was essential, but it stood apart. It did not mix with space. It simply ordered events, telling which came before and which came after. Modern physics changed that picture. It did not make everyday time disappear, and it did not say that ordinary clocks are meaningless. Instead, it showed that time is not as absolute as it seems. Measurements of time can depend on motion. Measurements of time can also depend on gravity. Two observers who move differently, or who sit in different gravitational conditions, may not agree perfectly on how much time has passed between the same events. This is not an illusion of perception. It is a real physical effect confirmed by precise measurements. The key shift is that space and time are connected. An event in the universe is not fully described by saying where it happens. We must also say when it happens. A flash of lightning, a heartbeat, a collision between particles, a signal reaching a telescope. Each event belongs to a location in space and a moment in time. Together, these form a single physical description. This combined structure is called spacetime. It is not simply space plus a clock beside it. It is a unified framework in which space and time relate to one another. This is why time is often called the fourth dimension. Not because it behaves exactly like the three dimensions of space, but because it is needed to locate events in reality. To describe where a stone is, three spatial directions may be enough. To describe an event involving the stone, such as the moment it touches the ground, time must be included. The event is not only somewhere, it is sometime. Without time, the description remains incomplete. Still, time has a special character. This is important. Calling time a dimension does not mean we can move through it as freely as we move through space. In ordinary space, directions are flexible. If a room is open, you can step forward, step back, move sideways, or climb upward. Time does not offer that kind of freedom. We seem to move from earlier to later, always in one direction. Physics treats time as part of the structure of events, but it also recognizes that time is different from space in the way it is experienced and measured. One way to understand this is to imagine your life as a path through space-time. You are not only an object occupying space, you are a continuing process extended through time. The child you once were, the person listening now, and the older version of you who may exist later are not all present to your senses at once. But in the language of space-time, they can be thought of as parts of a long path, sometimes called a world line. Every object has such a path. A planet traces a path through space-time. A beam of light traces a path. Even a quiet cup on a table is not frozen in reality. It continues from moment to moment, existing along time as well as within space. This way of thinking can feel strange because we usually experience only a thin slice of time. The present feels immediate. The past exists as memory and evidence. The future exists as possibility. But physics often describes events in a broader structure, where relationships between events can be studied without relying only on human feeling. In that structure, the question is not only how far apart two places are, but how events are separated in space-time. Two events may be separated mostly by space, mostly by time, or by a mixture of both. The speed of light plays a central role in this structure. Light is not merely fast. It sets a limit on how quickly information and influence can travel through the universe. Because of this limit, observers in different states of motion can disagree about certain measurements of space and time, while still agreeing on the deeper space-time relationship between events. This is one reason space-time is so important. It allows physics to remain consistent even when different observers describe space and time differently. For example, two events that seem simultaneous to one observer may not be simultaneous to another observer moving differently. This does not mean either observer is confused. It means simultaneity is not universal in the way common sense suggests. The idea that there is one cosmic present shared everywhere is not part of modern relativity in the simple way we might expect. Instead, time is woven into the observer's motion and the structure of light signals. This is deeply unintuitive, yet it has been tested repeatedly and is part of the working foundation of modern physics. Gravity adds another layer. In the modern understanding of gravity, mass and energy shape space-time. A planet does not simply pull objects with an invisible string through empty space. Rather, the presence of mass changes the geometry around it, and objects move according to that geometry. This includes time. Clocks closer to strong gravity can run at a slightly different rate than clocks farther away. Near extremely dense objects, the effect becomes much stronger. Around black holes, time and gravity are linked in ways that stretch ordinary imagination. This connection between time and geometry is one of the reasons the idea of hidden dimensions feels less impossible than it first sounds. Physics has already taught us that dimensions are not merely a human convenience. They are part of how reality behaves. Space can curve, time can stretch, gravity can be understood through the shape of space-time. Once this is accepted, it becomes natural to ask whether the structure might be richer still. Extra dimensions, if they exist, would not be a rejection of known physics, but an attempt to extend the idea that geometry and physical law are deeply connected. At the same time, we should not confuse time with hidden spatial dimensions. Time is not hidden. We experience its passage constantly, even if we do not fully understand its nature. Hidden dimensions, by contrast, would be directions or degrees of structure that do not appear directly in ordinary experience. Time serves as a bridge in this video because it shows how physics can expand the idea of dimension beyond simple everyday space. It prepares the mind for the possibility that reality may contain aspects that are real but not obvious. There is also a difference between the time of relativity and the arrow of time. Relativity explains how time is measured and how it relates to space, motion, and gravity. The arrow of time concerns why we remember the past, but not the future, why broken cups do not reassemble themselves, and why heat flows from warmer things to cooler things in ordinary conditions. That deeper direction of time is strongly connected to entropy, the tendency for disorder or the number of possible microscopic arrangements to increase in isolated systems. This is not the main subject here, but it reminds us that time has more than one layer of meaning. It is both a dimension in physics and the quiet direction in which our lives unfold. For the purpose of hidden dimensions, the most important lesson is simple. A dimension is not always what intuition first says it is. Time does not feel like height, width, or depth, yet it is essential to describing events. It is not optional. It is built into the structure of modern physics. The universe is not merely a place where things happen. It is a space-time in which where and when are connected. And as you let that thought settle, there is no need to force the mind to hold the whole structure at once. Time can simply become soft again. Not a problem to solve, but a gentle current carrying the day away. The room is still, the night is patient, and for now it is enough to rest inside this small moment, moving quietly through the fourth dimension without effort. Chapter 5. The first ideas of extra dimensions. The first scientific ideas of extra dimensions were not born from fantasy, but from a serious attempt to make nature look simpler at a deeper level. Physicists were not trying to add strangeness to the universe for decoration. They were trying to understand why different forces exist, why they follow mathematical laws, and whether those laws might be different faces of one more basic structure. Extra dimensions entered physics as a bold possibility. Perhaps the world looks complicated because we are seeing only part of its geometry. To understand why this idea appeared, it helps to remember how powerful geometry had already become in modern physics. For a long time, gravity had been described as a force acting between masses. A planet pulled on a moon, Earth pulled on a falling stone, the sun guided the motion of the planets. This picture worked beautifully in ordinary conditions and remains extremely useful. But it left gravity as something acting across space, rather than something explained by the shape of space and time themselves. Then the understanding of gravity changed. Gravity could be described as the curvature of space-time. Massive objects were not merely pulling other objects through an empty stage. They were changing the stage itself. A planet moved around the sun because space-time around the sun had a particular geometry. Light bent near massive objects because its path followed the structure of space-time. This was a dramatic lesson. It showed that geometry was not just a tool for measuring the universe. Geometry could be the language of physical reality. Once that idea existed, a natural question followed. If gravity could be understood through geometry, could other forces also be understood that way? Could electromagnetism, the force behind light, electricity, magnets, chemical bonding, and much of ordinary matter, also emerge from the shape of a deeper structure? This was the dream that opened the door to extra dimensions. Electromagnetism was already known to be one of the great achievements of physics. It had unified electricity, magnetism, and light into a single framework. Electric charges create electric fields. Moving charges and changing electric fields relate to magnetic fields. Light itself is an electromagnetic wave. This unity was profound, but electromagnetism still seemed separate from gravity. Gravity was geometry. Electromagnetism was a field living within space-time. The question was whether both might come from an even larger geometry. Theodore Kaluza proposed a daring answer. He imagined adding one extra spatial dimension to the four-dimensional space-time used in relativity. Instead of describing the universe with 3 dimensions of space and 1 dimension of time, he considered a 5-dimensional framework. The additional dimension was not introduced as a place where people could travel or where stars could hide. It was introduced mathematically as another direction in the structure used to describe reality. The remarkable result was that when the mathematics of gravity was written in this five-dimensional form, part of it resembled ordinary gravity and another part resembled electromagnetism. In other words, what looked like two different physical forces in four-dimensional space-time seemed to fit together as aspects of one higher dimensional geometry. This was extraordinary. It suggested that electromagnetism might not be separate from geometry after all. It might be a shadow or a visible part of geometry in a dimension beyond ordinary experience. This did not prove that the extra dimension existed, but it showed something powerful. Extra dimensions could do useful scientific work. They could organize physical laws in a surprising way. They could make separate ideas appear connected. The extra dimension was not merely an imaginative add-on. It produced a mathematical relationship that seemed meaningful. Still, there was an immediate problem. If there is another spatial dimension, why do we not experience it? Why can we move left and right, forward and backward, up and down, but not along this additional direction? Why does the world not feel five-dimensional? The theory needed an answer, because a large, ordinary extra dimension would likely be obvious. It would change motion, gravity, and the behavior of matter in ways we would notice. Oscar Klein later offered an important idea. Perhaps the extra dimension is not large and open like the three dimensions of space around us. Perhaps it is curled into a tiny loop at every point in space. If the loop is extremely small, then ordinary objects cannot move through it in any noticeable way. It would be present but hidden by its size and shape. This idea is often called compactification, though the word itself simply means that a dimension can be finite and wrapped up rather than extended outward without limit. A familiar image can help as long as we use it carefully. Imagine a long garden hose seen from very far away. From a distance, it may look like a thin line, something moving along it seems to have only one direction available, along the length of the hose. But up close, an insect could also move around the circular surface of the hose. The circular direction was always there, but it was too small to matter from far away. In the same spirit, an extra dimension could exist at every point while remaining too tiny for ordinary motion to reveal. This idea changed the meaning of hidden dimensions. A hidden dimension did not have to be somewhere else. It could be everywhere, but curled up so tightly that it escapes direct experience. This was a beautiful answer to the question of invisibility. It also connected with the emerging quantum understanding of nature. At tiny scales, certain physical properties come in discrete amounts rather than a continuous range. Klein's version of the idea tried to relate the small curled dimension to such quantum behavior, though the full picture was far from complete. The Kaluza-Klein idea was elegant, but it did not become a complete theory of nature. It did not explain all forces. It did not predict the full variety of particles that later physics discovered. It did not solve every problem created by combining gravity with the quantum world. For a time, it became more of a fascinating possibility than a central theory, but it left behind something extremely important: the idea that extra dimensions could unify physics. That idea survived because it touched a deep desire in science. Nature often looks simpler when seen from a broader perspective. Electricity and magnetism once looked like separate phenomena, then became parts of electromagnetism. Space and time once looked separate, then became spacetime. particles and fields, energy and mass, waves and matter all became connected in ways that earlier generations would have found surprising. Extra dimensions offered another possible step in this pattern. Perhaps forces that seem different in our ordinary view are related in a higher dimensional view. This is why the early history of extra dimensions matters. It shows that the idea was not invented simply to make science sound mysterious. It came from the search for unity. It came from the attempt to take geometry seriously after the success of relativity. If the shape of space-time could explain gravity, then perhaps a richer shape could explain more. There is also a useful caution here. A theory can be beautiful and still not be confirmed. The early extra-dimensional idea was mathematically suggestive, but nature is not required to follow every elegant equation. Science must ask whether a theory makes contact with observation. Can it predict something measurable? Can it explain known facts better than other theories? Can it survive experimental tests? The Kaluza-Klein approach inspired generations of thought, but it did not provide final proof of an extra dimension. Even so, its influence reached far beyond its original form. Later theories, especially those trying to connect gravity with quantum physics, would return to the idea that extra dimensions might be essential rather than optional. String theory, for example, would make extra dimensions central to its mathematical structure. Brain world ideas would later imagine our visible universe as part of a larger, higher dimensional setting. These later developments are more complex, but they carry the same old question. What if the universe becomes simpler only when seen from more dimensions than we can directly perceive? The first ideas of extra dimensions therefore occupy a special place in physics. They are early, incomplete, and uncertain, but also deeply creative. They show how scientists use imagination under discipline. The imagination suggests a hidden direction. Mathematics tests whether that suggestion has structure. Observation then decides whether nature agrees. This balance between boldness and restraint is what keeps the idea scientific. For the listener, the most important point is gentle and clear. Extra dimensions were first taken seriously because they offered a new way to think about unity. They suggested that what appears separate in our world may be connected in a deeper geometry. Gravity and electromagnetism did not become fully unified through the original theory, but the attempt itself opened a path. It gave physics a new question, and that question still echoes through modern research. And now, as the mind rests with this history, there is no need to chase every detail. It is enough to imagine science quietly following a thread through the dark, asking whether the universe might be simpler than it looks and larger than it feels. Let that thought become soft. Let the old questions settle into the silence of the night, where even the hidden shapes of reality can wait patiently until morning. Chapter 6. Why hidden dimensions might be curled up too small to see. Hidden dimensions might remain unseen, not because they are far away, but because they could be folded into the fabric of space at scales far beyond ordinary perception. This is one of the most important ideas in the science of extra dimensions. It changes the question from where are they to how are they shaped. If another dimension were large and open like the familiar directions of space, it would almost certainly affect the motion of objects, the spread of light, the strength of gravity, and the behavior of matter. We would not need subtle experiments to notice it. It would be part of daily life. So if extra dimensions exist and still escape us, they must be hidden in a more delicate way. The usual scientific idea is that an extra dimension could be compact. Compact does not mean imaginary. It means finite in a special geometric sense. Instead of stretching outward without obvious end, it closes back on itself. A simple circle is compact because if you travel around it far enough, you return to where you began. You do not reach an edge. You do not fall off. The direction is real, but it loops. In theories with compact extra dimensions, the hidden directions may behave somewhat like this. They may be present at every point in space, yet wrapped into tiny closed shapes rather than extended like the dimensions we move through. This can sound difficult because our imagination wants every direction to look like a hallway. We picture left and right, forward and backward, up and down, and then we try to imagine another direction sticking out somewhere. But compact dimensions are not usually imagined as extra corridors beside ordinary space. They are more like tiny geometric possibilities attached to every point. If you could magnify space far beyond anything available to human senses, the point might not be a simple featureless point. It might have hidden structure, a tiny internal shape with directions that ordinary objects cannot explore. To make the idea gentler, think of a tiny closed path, so small that from far away it collapses into what looks like a single point. A traveler small enough to move along that path would find a real direction, but after going far enough, would return to the starting place. To a much larger observer, that entire closed direction would be invisible. Compact extra dimensions are not tiny paths drawn inside ordinary space, but the comparison helps. A dimension can be real and still fail to appear in ordinary experience if its scale is small enough. The word scale is crucial. Human beings live at a particular scale of nature. Our hands are sensitive to grains of sand, smooth glass, rough wood, and flowing water, but not to the internal structure of atomic nuclei. Our eyes see patterns created by light, but not individual atoms directly. Even microscopes must use indirect methods to reveal the very small. Nature has many layers. Something can be real, measurable in principle, and still completely hidden from everyday senses. Compact dimensions would belong to an even deeper layer than the ones we usually imagine. Why would small size hide a dimension? The reason is that exploring something requires energy, resolution, and access. If a feature is much smaller than the scale of the probe used to examine it, the probe may pass over it as if it were smooth. A finger cannot feel the atomic lattice of a crystal. Visible light cannot reveal details much smaller than its own wavelength in the usual way. A low-energy particle may not respond to a compact dimension if it cannot be excited into motion along that hidden direction. The dimension is not gone, it is simply unavailable to that kind of probe. In higher dimensional theories, motion along a compact dimension can sometimes appear to observers like a new property of particles. Because the dimension is closed and tiny, motion around it may be restricted to certain allowed patterns. Those patterns could look, from our lower dimensional viewpoint, like heavier versions of familiar particles or new states that require very high energy to produce. This is one reason particle experiments are sometimes discussed in connection with extra dimensions. If hidden dimensions exist at accessible scales, they might leave traces through unusual particles, missing energy, or small deviations from expected behavior. So far, no confirmed evidence has shown that this is happening. Gravity is also important in the search for hidden dimensions. Gravity is much weaker than the other fundamental interactions at ordinary particle scales, and some theories have wondered whether this weakness might be related to extra dimensions. If gravity can spread through more dimensions than ordinary matter can, then it may appear diluted in the space we experience. In some models, this idea allows extra dimensions to be larger than the tiniest scales usually imagined, while still remaining difficult to detect. These ideas are speculative, but they show that compact dimensions are not only abstract geometry, they can be tied to physical questions about the strength of forces. However, if extra dimensions exist, they cannot be curled up in just any random way. The geometry matters. The size, shape, and symmetry of compact dimensions would influence the physics seen in ordinary space. In some theories, different compact shapes could lead to different particles, different force patterns, or different possible values for physical quantities. This is part of what makes the subject both powerful and difficult. A tiny hidden geometry could have enormous consequences, but there may be many possible geometries, and science must find ways to decide whether any of them correspond to our universe. This is especially important because a hidden dimension is not like an object placed inside the universe. It is part of the underlying stage on which physical events occur. If the compact shape were different, the low-energy world we observe might also be different. The particles that exist, the way forces behave, and the stability of matter could all depend on the deeper structure. This is one reason hidden dimensions are so interesting to theoretical physics. They offer a way to connect geometry with the features of the material world. At the same time, the idea must be treated carefully. Saying that dimensions are curled up is not a confirmed description of nature. It is a hypothesis used in certain theoretical frameworks. It helps explain why extra dimensions, if they exist, are not obvious. It also helps build mathematical models that attempt to connect gravity with the quantum world. But until a testable prediction is confirmed, compact dimensions remain possible, rather than proven. This distinction is important. Science can explore a hidden structure without claiming it has already found it. There is also a common misunderstanding worth clearing away. Curled up dimensions are not curled in the ordinary visual sense, like a ribbon twisted inside a room. The phrase is a human-friendly translation of a mathematical idea. The extra dimension is compact because its geometry closes on itself. Its smallness means ordinary motion does not reveal it. Our minds picture coils and loops because those images help, but the real geometry may be far more complex than anything easily drawn. Some compact spaces used in advanced theories have intricate shapes that cannot be faithfully represented in ordinary three-dimensional images. Another misunderstanding is the idea that hidden dimensions would be somewhere inside atoms. That is not quite right. They would not be little containers hidden in matter. They would belong to space itself at every location. Atoms would exist within the ordinary dimensions we know, while the compact dimensions would be part of the deeper background structure. If they exist, they would be present in empty space as much as inside matter. They would not be tiny objects. They would be tiny directions. This is a strange but important distinction. A tiny object has a location. A tiny compact dimension would be part of the way location itself is structured. It would not be found by cutting matter into smaller pieces, as if one could open an atom and see an extra curled direction inside. It would be inferred through its effects, if those effects exist and can be measured. Science often works this way. Many deep features of nature are known not because they can be seen directly, but because their influence leaves patterns in what can be observed. The reason hidden dimensions are so hard to detect is therefore not mysterious in a supernatural sense. It is a matter of scale, geometry, and interaction. If ordinary particles cannot move freely through them, if their size is extremely small, and if their effects appear only at energies beyond current experiments, then they may remain invisible for now. They could still influence the deeper consistency of physical law, but not in a way that appears in everyday life. And this brings us back to the quiet elegance of the idea. The familiar space around you may seem smooth, continuous, and simple. Yet theoretical physics allows the possibility that at unimaginably small scales, space may have hidden folds of structure. Not folds you could touch, not rooms you could enter, but compact directions woven into the geometry beneath experience. For now, there is no need to picture them perfectly. It is enough to let the idea rest gently in the mind. Reality may be smooth to us because we are large, slow, and human, moving through only the dimensions life has taught us to notice. The smaller structures can remain quiet tonight. The room can stay still, the darkness can stay soft, and whatever hidden shapes may lie beneath space can wait peacefully beyond the reach of thought. Chapter 7: String Theory and the Need for More Dimensions. String theory brings hidden dimensions into the story because, in this approach, extra dimensions are not added as decoration. They arise from the attempt to make the deepest laws of nature mathematically consistent. The basic idea begins with a simple change in how we imagine the smallest ingredients of matter. Instead of treating fundamental particles as point-like dots with no internal size, string theory imagines them as tiny one-dimensional objects. These objects are called strings, not because they resemble ordinary strings in a physical sense, but because they have length while being incredibly small compared with anything we can directly observe. In ordinary particle physics, an electron is treated as a point-like particle. It has properties such as mass and electric charge, but it is not pictured as a tiny ball with a surface. String theory changes the picture. A particle would be what a string looks like when observed at energies too low to reveal its extended nature. Different particles would not be made from different kinds of basic material. Instead, they could be different vibrational states of the same underlying type of object. In this view, the difference between one particle and another is somewhat like the difference between tones produced by the same instrument. The instrument is the same, but the pattern of vibration is different. This image is useful, but it must be handled carefully. Strings in this theory are not elastic threads floating through ordinary space. They are mathematical objects whose behavior is described by quantum rules. They may be open, with two ends, or closed, forming loops. Their possible vibrations depend on the structure of the space in which they move, and this is where dimensions become essential. A string has more ways to vibrate when the space around it has more directions. The number of dimensions is not a casual choice. It affects whether the theory remains self-consistent when quantum mechanics is applied. That word, consistency, is central. A physical theory must not merely sound interesting. It must avoid internal contradictions. It must not predict impossible probabilities. It must preserve the relationships required by quantum physics and relativity. In early string theory, researchers found that the mathematics only worked cleanly in particular numbers of dimensions. The simplest early version required many more dimensions than our everyday world appears to have. Later, more physically promising versions, involving a deeper symmetry between different kinds of particles, required 10 dimensions of spacetime, 9 dimensions of space, and 1 of time. This result is often misunderstood. It is not that scientists looked around, failed to explain something, and simply guessed that there were extra dimensions. Rather, when they tried to build a quantum theory of strings that behaved properly, the equations themselves placed strong restrictions on the number of dimensions. Too few dimensions, and the theory loses the delicate balance it needs. Too many, or the wrong kind, and unwanted inconsistencies appear. Extra dimensions became necessary because the mathematical structure demanded room for the strings to behave consistently. This makes string theory very different from ordinary speculation. It does not say, perhaps there are more dimensions, because that sounds mysterious. It says that if the fundamental objects are strings, and if those strings are to obey the rules of quantum mechanics and relativity in a consistent way, then the full framework naturally points beyond the four-dimensional spacetime we experience. The extra dimensions are part of the machinery that allows the theory to work. But there is a clear problem. We do not experience 9 spatial dimensions. We experience 3 large spatial dimensions along with time. So string theory must explain why the additional dimensions do not appear in daily life. The usual answer is that the extra spatial dimensions are compactified. They may be curled into extremely small geometric shapes, present everywhere but not accessible to ordinary motion. This connects with the earlier idea of hidden dimensions, but string theory makes the shape of those hidden dimensions especially important. In many versions of string theory, 6 extra spatial dimensions are imagined as forming a compact internal space. This internal space is not just a tiny decorative addition. Its geometry can influence the possible vibrations of strings. And because string vibrations are associated with particle properties, the shape of the compact dimensions could affect what particles exist, what masses they have, and how forces appear at low energies. In other words, the hidden geometry may help determine the visible physics. This is one of the most fascinating parts of the idea. The world of familiar particles may depend on the shape of dimensions we cannot see. The electron, the quark, the force carriers, and the patterns of interaction might be linked to deeper geometry. The compact dimensions would act almost like an unseen instrument whose shape determines the notes that can be played. We hear the notes as particles and forces, but the instrument itself remains hidden. Physicists have explored special kinds of compact shapes that are mathematically suitable for preserving important features of the theory. Some of these shapes are extraordinarily complex. They cannot be pictured accurately as ordinary objects in three-dimensional space. Illustrations may show folded, twisting forms with holes and curves, but these are only visual suggestions. The real structures are higher dimensional geometries. Their role is not to be beautiful on a page, but to allow a lower dimensional universe like ours to emerge from a higher dimensional theory. Another reason string theory attracted attention is that it naturally includes a particle-like vibration associated with gravity. In quantum theory, forces are often described through particles that carry interactions. A consistent quantum description of gravity would involve a particle associated with gravitational waves and the gravitational field. String theory contains such a vibration among its possible states. This was one of the reasons scientists began to see it not just as a theory of certain particles, but as a possible framework for quantum gravity. Quantum gravity is difficult because the best theory of gravity and the best theories of microscopic particles use very different languages. Gravity is described through the geometry of spacetime, while the small-scale world is described through quantum fields and probabilities. When physicists try to apply ordinary point-particle methods to gravity at extremely high energies, serious mathematical problems appear. Strings soften some of these problems because they are extended objects rather than infinitely sharp points. Interactions are spread out along tiny lengths rather than concentrated at exact points. This does not solve every problem automatically, but it gives the theory a structure that can handle gravity in a different way. Extra dimensions are woven into this effort. They help the theory maintain consistency, allow the right kinds of vibrations, and provide a framework in which gravity and other interactions might be described together. In this sense, the need for more dimensions is connected to the ambition of string theory itself. The theory is not merely trying to describe one particle or one force. It is trying to describe a deeper level from which particles, forces, and spacetime may all arise. Still, string theory remains unconfirmed as a description of nature. This must be said clearly. It has not produced direct experimental evidence showing that strings exist or that extra dimensions have the forms the theory suggests. The energies needed to reveal strings directly may be far beyond what current technology can reach. Many different compact shapes may produce different possible low-energy worlds, which makes it hard to extract one unique prediction. For this reason, string theory is both admired and debated. It is mathematically rich and deeply influential, but its connection to direct experiment remains challenging. Some researchers view this as a temporary difficulty caused by the enormous gap between human technology and the tiny scales where strings would become visible. Others worry that if too many compact shapes are possible, the theory may struggle to make sharp predictions about our particular universe. Both views are part of the honest scientific conversation. The theory is not accepted as established fact, but it remains important because it gives physicists a controlled way to ask questions that are otherwise extremely difficult. This does not make the idea useless. Even when unconfirmed, string theory has changed how physicists think about black holes, quantum gravity, geometry, and the relationship between different physical theories. It has revealed surprising links between areas of mathematics and physics that once seemed separate. It has shown that extra dimensions can be more than an optional hypothesis. They can become part of the internal logic of a serious attempt to understand reality at its deepest scale. For the topic of hidden dimensions, the lesson is clear. String theory needs more dimensions because its strings require a larger arena to vibrate consistently. If the theory is right in some form, then the three-dimensional space we know may be only the large, visible part of a richer dimensional structure. The remaining directions could be compact, silent, and woven into every point of the world, shaping physics from beneath the surface. And tonight, there is no need to hold all of that complexity at once. You can simply imagine the universe as a quiet instrument deeper than the senses can hear, with hidden dimensions forming part of its unseen shape. Let the thought be gentle rather than heavy. Let the day loosen. Let the mind grow still and allow the mystery to remain soft in the background, like a distant note fading into the dark. Chapter 8. Branes, Higher Dimensional Space, and the Universe as a Surface. The idea of branes asks us to imagine something both strange and carefully scientific. That the universe we experience may be like a surface embedded within a larger, higher dimensional reality. This does not mean our world is flat in the everyday sense, and it does not mean stars and galaxies are painted onto a sheet. It means that, in some theoretical models, the particles and forces that make up ordinary matter may be confined to a lower dimensional structure, while a larger surrounding space could exist beyond the directions we can move through. The word brane comes from membrane, but physicists use it in a more general way. A membrane in daily life is usually a thin surface, like a film or a flexible sheet. In theoretical physics, a brane can have different numbers of dimensions. It can be like a point, like a line, like a surface, or like something with 3 spatial dimensions. If our visible universe were described as a brane, it would not be a 2-dimensional sheet. It would be a 3-dimensional spatial world, extended in the directions we know, with time included in the history of events. From inside it, everything would feel normal. Space would still have depth. Bodies would still have volume. Planets would still orbit stars. The surface idea is not about making our world visually flat. It is about how our universe might sit inside a larger dimensional setting. This larger setting is often called the bulk. The bulk is the higher dimensional space in which a brane could be embedded. If that sounds abstract, imagine a page inside a room. A creature restricted to the page might know only the page's surface, even though the room has another direction beyond it. The page is not the whole room, but for the creature, it is the entire accessible world. Brane world models use a more advanced version of this idea. Our universe would not be a literal paper sheet, but it could be a lower dimensional region inside a broader structure. One reason this idea became important is that string theory does not only contain strings, it also contains branes. In some versions of the theory, open strings can have endpoints that are attached to branes. This is a powerful idea because it gives a possible explanation for why certain particles and forces might remain confined to our universe, even if extra dimensions exist. If the particles associated with ordinary matter are tied to strings whose ends are stuck on a brane, then those particles cannot simply wander freely into the higher dimensional bulk. They remain trapped within the structure we experience as our universe. Gravity may be different. In many brane world models, gravity is not confined in the same way as ordinary matter. Because gravity is associated with the geometry of spacetime itself, it may be able to extend into the bulk. This possibility has deep consequences. It could help explain why gravity seems so weak compared with other fundamental interactions. If gravity spreads through more dimensions than the forces holding atoms and light to the brane, then from our perspective, it may look diluted. It is not necessarily weak at the deepest level. It may only appear weak because part of its influence extends into dimensions we do not directly access. This is one of the most fascinating reasons scientists have studied branes. They offer a way to think about a long-standing puzzle. Why gravity is so much weaker than the other forces at small scales. A small magnet can lift a metal object against the gravitational pull of the entire Earth. That simple observation shows how weak gravity appears in ordinary situations. Brain world theories ask whether this weakness might be connected to higher dimensional geometry. The answer is not known, and no model has been confirmed as the final truth, but the question is scientifically meaningful. Brains also change how we imagine hidden dimensions. Earlier, we explored the idea that extra dimensions might be curled up too small to see. Brain world models offer another possibility. Extra dimensions might be larger than expected, perhaps even extended in ways we cannot freely enter, because ordinary matter is confined to a brain. In this picture, we do not fail to see the extra dimension only because it is tiny. We fail to move through it because the particles making up our bodies, instruments, and light are restricted to the brain. It is like being made of page-bound material in a world where the page sits inside a larger room. This does not mean we could step off the brain with the right machine. In these theories, confinement is not a matter of poor technology. It would be part of the fundamental behavior of particles and fields. If the particles of ordinary matter are tied to the brain, then every tool we build from ordinary matter is tied to it as well. The limitation is not like a locked door waiting for a key. It is more like the rules of what our matter is. The idea of the universe as a brain also affects cosmology, the study of the universe as a whole. If our universe is embedded in a higher dimensional bulk, then the early universe might have involved brain motion, brain interactions, or effects from higher dimensional gravity. Some speculative models have even imagined cosmic events involving brains as possible ways to think of the beginning or evolution of the universe. These ideas are highly theoretical and not established facts, but they show how brains can turn hidden dimensions from a small-scale particle question into a cosmic question. At this point, it is important to separate careful science from popular exaggeration. Brain world theories are sometimes described as proof of parallel universes or nearby hidden worlds. That is not correct. Some mathematical models contain multiple brains, and one could imagine other brains existing in the same larger bulk. But this is not evidence that another universe is floating next to ours in any directly confirmed sense. It is a theoretical possibility inside certain frameworks, not an observed reality. The science is interesting enough without turning it into certainty. The surface analogy also has limits. If our universe is a brain, it would not necessarily have an edge that could be reached by traveling far enough. A surface can be finite without an edge, like the surface of a sphere, and higher dimensional geometry can behave in ways that do not match simple pictures. When we say the universe might be a surface, we do not mean there is a border where galaxies stop and the bulk begins. The relationship would be more subtle. The brain would be the arena in which our matter and light exist, not necessarily a visible sheet with a rim. In some brain world models, the geometry of the bulk is not plain and simple. It can be warped, meaning distances and gravitational effects change in a way shaped by the higher dimensional structure. Warped geometry can make gravity behave as though it is mostly concentrated near our brain, even if an extra dimension is not curled up in the simplest way. This was an important insight because it showed that extra dimensions might hide not only through small size, but through geometry itself. The shape of the bulk can control what we experience on the brain. This connects back to a recurring theme. Geometry is not just background decoration. In modern physics, geometry can influence forces, motion, and the behavior of fields. Branes extend that idea. They suggest that the universe we observe might be a region where certain fields are localized, while the deeper geometry around it shapes what happens within it. The world we know could be real and complete for everything made of ordinary matter, yet still be part of a larger structure that only gravity, or perhaps very high-energy processes, can reveal. How could such an idea be tested? Scientists have considered several possible clues. If gravity behaves slightly differently at very small distances, that might suggest extra-dimensional effects. If high-energy particle collisions produce signs of energy leaving the brain, that could be interpreted as a possible hint, though no confirmed evidence has appeared. Cosmological observations might also constrain brain world models by checking whether the early universe evolved in ways consistent with ordinary physics. So far, the familiar picture of particle physics and cosmology remains extremely successful, and brain world ideas remain hypothetical. But hypothetical does not mean meaningless. Many scientific ideas begin as disciplined possibilities before evidence decides their fate. Branes gave physicists a new language for thinking about localization, extra dimensions, gravity, and the relationship between visible and hidden structure. They help turn the question of extra dimensions from a simple question of where they are into a richer question of what kind of higher dimensional world could make our familiar universe appear the way it does. For a listener, the most useful image is gentle but precise. Imagine that everything you know, every star, every atom, every wave of light, may belong to a vast three-dimensional surface of experience. Not a flat illusion, not a fake world, but a real physical arena. And around that arena, in certain theories, there may be a deeper bulk, a higher dimensional space that shapes gravity and structure without being directly available to touch or sight. This does not make ordinary life less real. It makes it more mysterious. The room around you, the quiet air, the softness of night, and the distant stars all remain part of the same familiar universe. If brains exist, they do not erase this world. They simply suggest that this world may be held within a wider geometry than the senses can follow. So let the idea become light. You do not need to picture the bulk or step beyond the brain or solve the shape of reality before sleep. For now, it is enough to rest on the surface you know, surrounded by a universe that may be deeper than it appears, while the night quietly carries the mind towards stillness. Chapter 9. Could hidden dimensions be tested? Hidden dimensions can only become science if they can, in some way, leave a trace that the universe allows us to measure. This is the difference between a mysterious idea and a scientific hypothesis. A hidden dimension may be too small to see, too tightly curled to enter, or too inaccessible for ordinary matter to move through. But if it belongs to physical reality, it should affect something. It might change gravity at tiny distances. It might alter the behavior of particles at very high energies. It might influence how gravitational waves travel across the cosmos. Testing hidden dimensions means looking for those faint fingerprints, not trying to see another direction with the eyes. The challenge is that hidden dimensions, by definition, are not obvious. If they were large and freely available to ordinary matter, daily life would already reveal them. Objects would have more ways to move. Forces would spread differently. The structure of atoms, planets, and light would not match what we observe. So any serious test must begin with a careful question. What would hidden dimensions change while still remaining hidden from ordinary experience? The answer depends on the theory. Different models predict different signals, and this is why there is no single universal experiment that can settle every version of the idea at once. One of the clearest places to look is gravity. Gravity is deeply connected to the geometry of space-time. So if space-time has hidden structure, gravity may be especially sensitive to it. In ordinary conditions, gravity becomes weaker with distance in a very predictable way. This behavior has been tested across enormous ranges, from falling objects to planetary motion. But some extra-dimensional models suggest that at extremely short distances, gravity might begin to behave slightly differently. If hidden dimensions open up below a certain scale, gravitational influence could spread into them, changing the strength of attraction between small masses. Testing this is extremely difficult because gravity is weak between small objects. The attraction between two tiny masses in a laboratory can be overwhelmed by vibrations, electric charges, temperature changes, air movement, and even tiny imperfections in the equipment. To search for deviations, scientists use very delicate instruments designed to measure faint gravitational forces at short distances. The goal is not to make gravity dramatic, but to see whether it follows the expected pattern even when the separation becomes very small. So far, these tests have not confirmed any departure that requires hidden dimensions. That does not prove hidden dimensions do not exist, but it rules out many versions that would have produced detectable changes at those scales. Another possible testing ground is high-energy particle collisions. Particle accelerators bring tiny particles together at enormous speeds and allow their energy to produce new states of matter. If extra dimensions exist, some theories predict that collisions could create heavier versions of known particles, sometimes described as echoes of motion through hidden dimensions. These would not be ordinary copies. They would appear as new particle states with specific masses and decay patterns. Detectors would search for unusual peaks, unexpected combinations of particles, or events that happen more often than known physics predicts. Some models also suggest that energy might appear to go missing in a collision. This does not mean energy is destroyed. In physics, energy must be accounted for. If a particle associated with gravity could move into extra dimensions, it might leave the ordinary region accessible to the detector. From our perspective, the event could look unbalanced, with visible particles carrying less energy than expected. Scientists already know how to account for ordinary invisible particles, so the search must be careful. Missing energy alone is not proof of hidden dimensions. It must appear in a pattern that cannot be explained by known particles or experimental uncertainty. There is also a more dramatic possibility, sometimes discussed in large extra-dimensional models. Very high-energy collisions might produce tiny black holes. This idea depends on specific assumptions about the true strength of gravity at small scales. If extra dimensions made gravity effectively stronger at high energies, microscopic black holes could become possible in particle collisions. These objects, if they existed, would be extremely short-lived and would decay into many particles almost immediately. No such evidence has been found. The absence of these events has helped place limits on the models that predicted them. Particle experiments are powerful, but they face a basic limitation. If the energy scale where hidden dimensions reveal themselves is far beyond our machines, then no present collider can reach it directly. This is common in fundamental physics. A theory may describe real structure at scales far smaller than current instruments can probe. In that case, scientists look for indirect signs, slight changes in known processes, rare events, or patterns that become clearer only after enormous amounts of data are collected. The difficulty is that the more indirect the sign, the more carefully it must be separated from ordinary physics. Cosmology offers another window. The early universe was extremely hot and dense, with energies far beyond anything found in ordinary life today. If hidden dimensions influenced particle behavior, gravity, or expansion during those early moments, they might have left traces in the large-scale structure of the universe. The distribution of galaxies, the abundance of light elements, and the faint afterglow from the early universe all provide tests of physical models. Extra dimensions cannot be added freely if they would disrupt what observations already show. Even without detecting a hidden dimension directly, cosmology can rule out possibilities that would make the universe evolve in the wrong way. Gravitational waves provide a newer kind of test. These waves are ripples in spacetime produced by extremely energetic cosmic events, such as merging black holes or neutron stars. Because they are disturbances of spacetime itself, they are natural messengers for testing the structure of gravity. Some theories with extra dimensions suggest that gravitational waves might lose energy into hidden directions, travel in slightly altered patterns, or show additional features beyond the predictions of ordinary general relativity. Observations so far have been consistent with the familiar four-dimensional description within current limits. But as gravitational wave astronomy becomes more precise, it may continue to test extra-dimensional ideas in ways that were impossible before. The important point is that a test does not always need to find something new to be useful. When experiments find no deviation, they still teach us. They narrow the range of possible hidden dimensions. They say that if such dimensions exist, they must be smaller, more weakly connected, more highly curved, or more carefully hidden than certain models allowed. Science advances not only through discovery, but also through exclusion. A theory that once had a wide open landscape becomes more constrained as measurements improve. This is why hidden dimensions remain both fascinating and frustrating. They are not impossible to test in principle, but they may be difficult to test in practice. Some versions predict effects that would be visible only at energies far beyond current technology. Others predict effects so small that they hide beneath experimental noise. Still others can be adjusted in ways that make them hard to rule out completely. For a theory to be scientifically strong, it must eventually make contact with observation. The more flexible a theory becomes, the harder scientists must work to identify what would count as a real test. There is also a danger in expecting one spectacular discovery to settle everything. The search for hidden dimensions is more likely to progress through many careful measurements. A small deviation in gravity would need confirmation. A strange particle signal would need to be distinguished from other new physics. A gravitational wave anomaly would need to be checked against astrophysical uncertainties. One measurement rarely carries the entire burden. Science builds confidence by seeing whether independent lines of evidence point in the same direction. For now, the honest answer is that hidden dimensions have not been confirmed. No laboratory, collider, telescope, or gravitational wave detector has provided accepted evidence that extraspatial dimensions exist. But the idea remains scientifically meaningful because it suggests possible effects and allows experiments to set limits. It is not merely a dream without consequences. It is a set of questions that nature can, at least in some forms, answer. This is a beautiful part of physics. Even when reality hides something, science asks how deeply it can hide. If dimensions are curled too small, we test shorter distances. If gravity might leak into a larger space, we listen to gravitational waves. If particles might reveal hidden motion, we study collisions at higher energies. Each method is like touching the edge of an unseen shape, not seeing it directly, but asking whether the shape pushes back. And as this chapter comes to rest, the mystery can remain gentle. Hidden dimensions do not need to be solved tonight. They can stay as a quiet question at the edge of knowledge, while the known universe continues to breathe around you in steady, familiar space. Let the search belong to tomorrow. Let the mind soften, and let the unanswered parts of reality become peaceful rather than heavy. Chapter 10. What hidden dimensions would mean for reality. If hidden dimensions exist, they would not simply add a strange detail to physics. They would change the way we understand what reality is built from. The world around us would still be real. The room, the body, the air, the stars, and the quiet darkness between galaxies would not become illusions, but they might become part of a larger structure, one where the dimensions we experience are only the broad, accessible directions of a deeper geometric world. This is the first important meaning of hidden dimensions. They would show that human experience is not the full measure of physical reality. Our senses are beautifully adapted to the scale of everyday life. We notice surfaces, distances, motion, weight, warmth, and light. We are good at navigating rooms, roads, landscapes, and skies. But we do not naturally perceive the smallest layers of matter, the curvature of space-time, or the quantum fields underlying particles. If extra dimensions exist, they would be another reminder that reality can be much wider than perception. The universe would not be limited to what the body can directly touch or picture. At the same time, hidden dimensions would not make ordinary life false. This is a common misunderstanding. When science reveals a deeper layer, it does not erase the layer above it. Atoms do not make tables unreal. Quantum fields do not make atoms meaningless. Space-time curvature does not make gravity as we feel it disappear. Each level remains valid in the right context. A chair is real for the body. An atom is real for chemistry. A field is real for modern physics. In the same way, our three large spatial dimensions would remain real even if they were part of a larger dimensional structure. The deeper meaning would be about completeness. We might have mistaken a partial view for the whole view. Our familiar space could be like a broad surface of experience, stable and consistent, while hidden directions quietly shape the laws that operate within it. This would be a profound shift. It would mean that the structure of the universe is not fully captured by the stage we move through. The stage itself may have hidden architecture. One of the most important consequences would involve the laws of physics. If hidden dimensions exist, they may not be passive. They could help determine the properties of particles and forces. In some theoretical frameworks, the shape and size of compact dimensions influence which particle states are possible, how fields behave, and why certain interactions have the strength they do. The visible world might depend on geometry that is not directly visible. What we call a particle could be related to a pattern in a deeper structure. What we call a force could reflect how fields move through or are restricted by that structure. This does not mean scientists already know the correct hidden shape. They do not. There are many possible geometries, and no confirmed evidence has shown that any specific one describes our universe. But the possibility itself is powerful. It suggests that laws may not be arbitrary rules written on top of nature. They may emerge from the form of nature. The universe may behave as it does because its underlying geometry allows certain patterns and forbids others. Gravity would become especially important in this picture. Gravity already teaches us that geometry and physics are connected. Massive objects curve space-time, and that curvature guides motion. If hidden dimensions exist, gravity might be a clue to the wider structure. In some models, gravity can spread into dimensions that ordinary matter cannot access. If so, the weakness of gravity compared with other interactions might not be an accident. It might reflect the way gravity occupies a larger dimensional arena. This would change the emotional shape of the cosmos. Gravity is the force that builds planets, stars, galaxies, and black holes. It organizes the universe on the largest scales. If gravity is also the messenger most sensitive to hidden dimensions, then the same force that holds galaxies together may be whispering about a deeper architecture beneath space. That idea remains speculative, but it is scientifically meaningful. It connects the smallest hidden structures with the largest visible ones. Hidden dimensions would also affect how we think about unity. Physics has often advanced by discovering that separate things are connected. Electricity and magnetism turned out to be aspects of one interaction. Space and time became part of one space-time structure. Matter and energy were shown to be deeply related. Hidden dimensions could represent another kind of unity. Forces and particles that seem unrelated in ordinary space might become connected when seen from a higher dimensional point of view. The world might look complicated because we are viewing a deeper simplicity from the inside. But this possibility must remain carefully balanced with uncertainty. Hidden dimensions have not been proven. No experiment has yet confirmed extra-spatial directions beyond the familiar ones. Theories that use them are attempts to solve real problems, especially the challenge of connecting gravity with quantum physics, but they remain incomplete as descriptions of nature. A calm scientific mind can hold both thoughts at once. Hidden dimensions may be real, and they may be deeply important. They may also turn out to be a beautiful mathematical path that nature does not take. If they are real, they would also change our idea of place. Usually, we imagine that to find something hidden, we must travel somewhere else. We search behind a wall, under a stone, beyond a horizon. But hidden dimensions may not be distant in that way. They may be present everywhere, not as objects within space, but as part of space's structure. The hidden would be intimate rather than remote. It would be here, beneath every ordinary location, folded into the meaning of location itself. This is one of the strangest ideas in the whole subject. The deepest hiddenness may not belong to faraway galaxies or unreachable cosmic edges. It may belong to the immediate world, to the space around your hand, to the silence between one breath and the next. If compact dimensions exist, then every point of ordinary space could contain more geometric structure than it seems. Not more in the sense of clutter, but more in the sense of depth. The human mind naturally wants to turn this into a picture. We imagine layers, tunnels, folded sheets, or secret rooms. These images can be useful, but they are not the reality itself. Hidden dimensions would likely not resemble anything the imagination can display directly. Their meaning would be mathematical and physical before it is visual. They would be known through effects, consistency, and measurement, not through a simple image in the mind. This is not unusual in science. Many real things are understood first by their relationships, not by direct visualization. There would also be philosophical consequences, though they should remain grounded. Hidden dimensions would not automatically prove mystical claims, nor would they show that anything imaginable must exist. Science does not work that way. A hidden dimension in physics is not a spiritual realm or a place where normal rules vanish. It is a precise idea about the structure of space, fields, and geometry. Its meaning is extraordinary enough without exaggeration. It would show that the natural world is deeper than common sense, not that common sense has no value. Perhaps the most humbling meaning is that reality may be layered. The world we experience may be one stable layer of a more complete description. Life happens in this layer. Thought happens here. Love, memory, work, fatigue, curiosity, and sleep all unfold in the dimensions we know. Even if hidden dimensions exist, they do not take us away from this world. They place this world within something larger. That larger structure may never become directly imaginable. It may always remain partly beyond the shapes our minds evolved to handle. But that does not make the search meaningless. To ask about hidden dimensions is to ask how much of nature lies beneath appearance. It is to admit that the universe may be more generous than perception, more subtle than language, and more organized than it first seems. So what would hidden dimensions mean for reality? They would mean that space is not merely emptiness. They would mean that geometry may be one of the deepest ingredients of the physical world. They would mean that what feels complete to us may still be a doorway into a wider structure. And they would mean that the familiar universe, with all its stars and distances, may be only the visible face of something quieter, older, and deeper. For now, the mystery can remain gentle. You do not need to solve the shape of all dimensions tonight. You can rest in the ones you know, the softness beneath you, the stillness around you, the slow passage of time carrying the day away. If reality has hidden depth, it will still be there tomorrow. Tonight, it is enough to let the thought widen softly, then fade into calm. And now, my friend, we've reached the end of our quiet journey through hidden dimensions. We've seen how something as familiar as space can become strange again when science looks deeply enough. The world around you may feel simple and complete, and in everyday life, it truly is. But beneath that familiar surface, physics leaves room for a deeper possibility. That reality may have hidden structure, folded quietly beyond what the senses can reach. If you're still awake and would like to keep drifting through the mysteries of science, you can watch another video and continue the journey with me. But if sleep is already near, let the questions rest for now. Let the universe remain wide, silent, and unfinished. Sweet dreams among the stars.